All right, hello. Today's lesson is going to be section 11.5, proportions with area. Our objectives are going to be able to understand and apply the area between similar figures using the similarity conjectures. So, recap, when we were given two similar figures, we could solve for a missing value. Before, we had looked at corresponding parts on similar triangles, but now we're going to be looking at any type of similar figure. So here you can see that we've got two pentagons, and they have to tell us that the figures are similar before we can proceed on. Now, up here, they said that we had two given similar figures. They could also use that similar marking, that little squiggly, to indicate that these figures do have the same scale factor for all of their corresponding parts. So if I'm looking at the side length here of 3 compared to the side length of 9, I know that there's going to be some sort of scale factor multiplying 3 to get to 9. And if you've already done it in your head, you might see that it's times 3. So if we're looking at the perimeter, the missing perimeter, we could say that there's the same scale factor because they have the same units. So I could say the perimeter of the first pentagon multiplied by 3 will equal the perimeter of the second pentagon. Now, sometimes thinking what times 3 is 45 is a little bit tricky, so we could go backwards as well. We could say 9 times 1/3, times 1/3 would get us the number 3. So 45 times 1/3 would also get us the perimeter of the small figure. Now, because we know that typically when we're shown pictures like this, it kind of looks like all of the side lengths are the same on these pentagons. We could probably just figure it out that way, but I'm not totally sure because there weren't markings or shown things saying that this was a regular pentagon. So we'll do this with the scale factor, and then I'll show you how to do it with the proportions. So I'm going to take 45 and multiply by 1/3, and I get the number 15. So that means that the perimeter of this pentagon is 15 centimeters. Now we could have also made a proportion, like I said before. I could say 3 compared to 9 is equal to the missing perimeter compared to the perimeter of 45. And here we could do our cross multiplying. 3 times 45 comes out to 135. Excuse me. 9 times x is 9x. We'll do a small t-chart. Divide by 9. 135 divided by 9 comes out to 15 as well. Now, you could have also looked at this picture and said, well, if I have a side length of 9 here, and all of these were 9s, 9 times 5 is 45. So I could have just done 3 times 5 to get 15. But they will not always be a regular polygon. Okay, now again, this works because centimeters for the side length is the same units as centimeters for the perimeter. But once we get to something like area, remember, is units squared. And we cannot compare square units to just plain units because they are two different measurements. So we're going to do this investigation to figure out how do areas compare to side lengths on similar figures. All right, again, knowing that these triangles are similar, so you could technically put that little squiggly mark saying that they are similar. We want to answer the following questions. What is the base length of triangle DEF? Well, DEF is this first triangle here, and the base is a length of 24. What is the base of triangle ABC? That's this one over here, and that is a length of 8. If I look at the comparison of those, the ratio, I'm going to do 24 divided by 8. And when I work that out, it comes out to the number 3. All right, let's look at the area of triangle DEF. Now, this is going to require some remembering of how do I find the area of a triangle. So area of a triangle is base times height divided by 2. So looking at the base of this first triangle, I see it has a base length of 24. I see that it has a height of 9. And if I divide by 2, that will get me the area of that triangle. So this area comes out to be 108 for triangle DEF. If I do the same thing for triangle ABC, the area is going to be the base of 8 times the height of 3 divided by 2. 8 times 3 divided by 2 comes out to be 12. All right, now let's compare these numbers in a ratio. 108 divided by 12. 108 divided by 12. Ooh, that comes out to the number 9. Now it wants me to compare our two ratio values. So looking at the ratios of the base lengths, that comparison came out to a ratio of 24/8, which was 3. The comparison of the areas in a ratio was 108/12, which came out to a measurement scale factor of 9. So if I'm looking at these ratios, I can see that the 3 compared to the 9 is actually multiplying by itself, by another 3. So here I have 2 3s, or 3 squared, to get that value of 9. Interesting, because when I think about area is units squared. So if I'm thinking about the units on these base lengths, maybe they were in centimeters. I could say 24 centimeters compared to 8 centimeters. But when I'm comparing areas, it would be centimeters squared. So if I want to compare the base ratios to the area ratios, they're not equivalent until I create the same type of units, centimeters to centimeters squared. All right, here is the conjecture. Excuse me. It says that if corresponding side lengths of two similar polygons, or we could consider the radii of two circles, compare in the ratio m/n. This would be like the side lengths or the base lengths that we compared up here, 24/8. Then their areas compare in ratio to that same fraction, but squared. That seems kind of confusing. So let's practice this on another example. So here it says, if we're going to be comparing them as squared units, it means that before we cross multiply or use scale factors to solve a proportion on similar figures, we need to make sure that all the values are in the same unit of measurement. For example, like I said before, centimeters versus centimeters squared. In this next picture, you can see we have 2 rectangles. Let's assume that these are similar figures. They didn't specify, but this only works when we have similar figures. And so here we have a base length of 4 inches compared to a base length of 8 inches. Then we are looking at their areas being compared, 6 inches squared to unknown inches squared. So what we need to do is we can set up the proportion the same as we had before. 4 inches compared to 8 inches equal to 6 inches squared compared to unknown inches squared. Now, before we can cross multiply, we need to make sure that our unit of measurement is the same. So since I only have inches on the left, I'm going to square these to make them inches squared. And 4 squared would be 16. And if I do 8 squared, 8 times 8 is 64. And then I'm going to keep the fraction on the right the same because it is already in inches squared. And then we are going to cross multiply now that all of the units are in the same unit label. So here we're going to do 64 times 6. And we will set that equal to 16 times x. All right, 64 times 6 comes out to 384, which is equal to 16x. Do a little mini t-chart, divide by 16. 384 divided by 16 gives us x equaling 24, which means the unknown area of this rectangle on the right is 24 inches squared. All right, let's jump down to example 2. Again, before we start, we would have to know that these figures are similar. So let's assume that these two trapezoids are similar. All right, here we've got a base of 6 inches compared to a base of 10 inches. The unknown area compared to the area of 120 inches squared. So I'm going to set up my proportion just like before. I'm going to start with 6 inches compared to 10 inches. And then we're going to compare the smaller trapezoid area, that is an unknown inches squared, to the larger trapezoid area of 120 inches squared. Okay, I would like to cross multiply, but I can see I have inches versus inches squared. So I need to make sure that I change everything to the same unit of measurement. I'm going to square the 6 and the 10 to create inches squared as a comparison. So 6 squared is 36, and 10 squared, or 10 times 10, is 100. And then those would still be the same as x inches squared over 120 inches squared. And then we cross multiply. So I'm going to do 36 times 120, and I get 4,320 inches squared when I multiply those together. I'm going to set that equal to 100 times x, which would just be 100x. And we do our mini t-chart. We would divide by 100 on both sides, divided by 100, and our x value comes out to be 43.2, which means the area of our original trapezoid on the left was 43.2 inches squared. All right, let's try another one. Example 3. This time we have a hexagon. In this hexagon, I can see that we have a side length of 9 compared to a side length of 2 centimeters. We are also comparing areas, unknown area in centimeters squared compared to 18 centimeters squared. So I'm going to start by making my ratio. 9 centimeters compared to 2 centimeters. It is going to be equal to our unknown centimeters squared for the area compared to 18 centimeters squared for the area. And we're going to cross multiply. Oh, wait, I can't cross multiply yet. I need to create all of these units the same. So I'm looking at missing centimeters squared. So let's square these plain centimeters. When I do that, I'm going to get 81 centimeters squared over 4 centimeters squared, which is equal to x centimeters squared over 18 centimeters squared. Now we can cross multiply. All right, 81 times 18 comes out to 1,458. And if I go the other direction, 4 times x is just 4x. I will divide by 4 on both sides. 1,458 divided by 4x turns out to be 364.5. So the area of the large hexagon is 364.5 centimeters squared. All right, example 4 is a little bit different. In this example, again, we have to assume that these are similar figures, but I notice that, the base length is what's missing this time, not the area. So when I'm comparing these two, I'm going to have a missing base length, x centimeters, compared to, I also have a typo here. It shouldn't say centimeters. This should say meters. Let's erase that. X meters compared to 10 meters. All right, now the comparison is going to be to the areas. So looking at the areas, I have 56 meters squared and 35 meters squared. Okay, now typically on the last ones, we were squaring the numbers so that they all matched with the area because the area was missing. But this time, we don't want it to be squared because we want to find the base length in meters. So there's a couple different ways that you can do this. We could get rid of the squares for the 56 meters squared and the 35 meters squared. But those are not perfect square numbers. And so it's going to come out to be kind of some ugly decimals. So instead, I'm just going to continue with that pattern and say, I'm going to square everything. So square it. This would give me x squared meters squared over 100 meters squared is equal to 56 meters squared over 35 meters squared. They're all in meters squared, so we can cross multiply. So if I cross multiply, I'm going to do 100 meters squared times 56 meters squared. And when I type that in, I get 5,600 meters squared. All right, going the other direction, x squared times 35 is going to actually be 35x squared. Let's see, I'm going to erase that label for now just to save on some space. 35 times x squared. All right, so let's do our t-chart. Got to get rid of the 35, so I'm going to divide by 35 on both sides. 5,600 divided by 35 comes out to 160, but this is not equal to x. It's equal to x squared. Now, we don't want units squared because we are looking for the base unit. So we need to get rid of the squared. The opposite of squared is square root. So if I square root 160, I'm going to get my x answer of approximately 12.6 units long. All right, and that concludes our lesson on finding different measurements with area related to similar figures.